Accelerating Java Microservice Deployment with AI-Driven Dockerization. Welcome, fellow engineers and tech enthusiasts, to a topic that's revolutionizing how we deploy our applications, accelerating Java Microservice Deployment with AI-Driven Dockerization. In today's fast-paced development landscape, microservices are the backbone of scalable, resilient systems. And when it comes to packaging and deploying these microservices, Docker has become an indispensable tool. But here's the often overlooked challenge: creating truly optimized Docker files for Java applications can be surprisingly complex and time-consuming. It involves deep knowledge of Java runtimes, JVM tuning, build processes, and Docker best practices for efficiency, size, and security. Manually tweaking these files for every new service or every change in best practices becomes a monumental task, leading to larger images, slower builds, and potential security vulnerabilities. Imagine a world where your Docker files aren't just boilerplate, but intelligently crafted blueprints, tailored for peak performance. This is where the power of generative AI steps in. AI can analyze your project, understand its nuances, and automatically recommend or even generate highly optimized Docker files. This isn't just about saving time, it's about elevating the quality, security, and efficiency of your deployment pipelines. Think of Gen AI as your expert co-pilot, guiding you to create container images that are smaller, faster, and inherently more secure, transforming a bottleneck into a seamless, automated part of your CI/CD process. Let's dive in and see how AI can truly revolutionize your Java microservice deployment. So, what exactly does this AI-driven approach look like, and how does it fundamentally change our deployment paradigm? Imagine having an intelligent assistant that understands the intricacies of Java applications, the nuances of Docker, and the latest best practices in containerization. This AI assistant doesn't just give you a generic template, it analyzes your specific Java project, its dependencies, framework, and even its execution profile, to suggest the most optimal Docker file. This isn't a future fantasy, it's a capability that generative AI tools are making possible today. By integrating an AI recommendation engine into your development workflow, you transform Docker file creation from a manual, expert-driven task into an automated, intelligent process. This dramatically reduces the cognitive load on developers, allowing them to focus on writing business logic rather than becoming Docker file optimization gurus. The result? Faster time to market, consistent application of best practices across your entire microservice fleet, and a significant boost in developer productivity. It's about leveraging the power of machine intelligence to make our existing processes smarter and more efficient. But why go through all this trouble? Why do optimized Docker files truly matter in the grand scheme of software deployment? The benefits are multifaceted and directly impact your operational efficiency and bottom line. Firstly, smaller image sizes mean faster pulls, quicker deployments, and reduced storage costs on your container registries. Think about hundreds or thousands of microservice deployments daily, those megabytes add up to terabytes. Secondly, enhanced security is paramount. An optimized Docker file eliminates unnecessary components, runs processes as non-root users, and applies secure configurations, drastically reducing the attack surface of your containers. Thirdly, faster build times are a CI/CD dream. When your Docker builds are lean and efficient, your entire pipeline runs quicker, leading to faster feedback loops and accelerated development cycles. Lastly, improved runtime performance is a direct result of fine-tuned JVM settings and a minimal runtime environment, ensuring your Java applications consume fewer resources and respond faster. These aren't just theoretical advantages, they translate into tangible improvements in reliability, cost-effectiveness, and peace of mind for your operations teams. It's about building robustness into your deployment strategy from the ground up. Now, let's zoom in on Java. While Docker offers incredible benefits, Java applications bring their own set of unique challenges when it comes to containerization. Unlike lightweight compiled languages, Java applications often produce large, fat, jar files that bundle all dependencies. This can lead to bloated Docker images if not handled carefully. Furthermore, the Java Virtual Machine, or JVM, itself requires careful tuning within a containerized environment. Default JVM settings might not be optimal for constrained container resources, potentially leading to excessive memory consumption, slow startup times, or even dreaded out-of-memory error exceptions. Developers often spend considerable time experimenting with base images, multi-stage builds, and arcane JVM flags like XMS, XMX, and use container support to get it just right. This manual fine-tuning for each microservice, across different environments, can become a significant bottleneck. This is precisely where an AI-driven approach shines brightest. AI can understand the intricacies of Java's runtime behavior and intelligently recommend Docker file configurations that account for these unique challenges, ensuring your Java microservices run optimally within their containerized homes. So, how does this magical AI-driven Docker file generation actually work? Conceptually, it's quite elegant. When a developer commits their Java microservice code to a Git repository, it kicks off your standard CI/CD pipeline. But here's the game-changing twist: before the traditional Docker image build step, we introduce an AI-driven Docker file recommendation stage. This stage invokes a specialized AI script or service. This AI doesn't just guess, it performs a sophisticated analysis. It examines your Java project, its Maven pom.xml4 dependencies, the Spring Boot version, and even the compiled JR artifacts characteristics. Based on this deep understanding, coupled with pre-configured optimization goals like image size, build speed, and security posture, the AI generates a highly optimized Docker file. In our demonstration, this is simulated by a Python script, recommend_dockerfile.py, which outputs a file named dockerfile.recommended. This AI-generated Docker file then becomes the blueprint for the subsequent Docker image build. This ensures that every image built by your pipeline is inherently optimized, consistent, and adheres to the latest best practices, all without manual intervention. Let's peel back the layers and look at what makes an AI-optimized Docker file so effective, focusing first on the crucial concept of multi-stage builds. Traditional, single-stage Docker files for Java applications often result in bloated images because they include the entire Java Development Kit, JDK, Maven, and all build tools within the final runtime image. This is like moving your entire workshop into your finished house. An AI, understanding this inefficiency, will recommend a multi-stage build strategy, as seen in our dockerfile.recommended. The first stage, often named build, uses a comprehensive JDK base image, like Eclipse Demurin, 17, JDK, Focal, and all necessary tools to compile and package your Java application. Crucially, in the second stage, typically named final or runtime, the AI switches to a much lighter Java runtime environment, JR, base image, like Eclipse Demurin, 17, JR, Focal. Only the lean, executable JR artifact is copied from the build stage to this final runtime stage. This separation ensures that your production image contains only what's absolutely necessary to run the application, significantly reducing its size, improving security by removing unnecessary attack vectors, and speeding up deployment times. The AI's genius lies in orchestrating these stages perfectly for optimal results. Beyond multi-stage builds, an AI-optimized Docker file implements other clever techniques to enhance build speed and security. Consider layer caching. Docker builds images